How are we doing today? Hopefully, y'all are doing well. So, today we are going to be starting our unit for notes. All right. And for this, we are going to be continuing into Intro to Chemical Reactions. Now, this should be review from you from your previous chemistry course. If it's not, you're going to have just a little bit of catching up to do. But otherwise, we are going to go ahead and get started on this. For this, you do need to make sure you've got your notes, something to write with, and then I would highly suggest a periodic table as well. All right, so let's go ahead and get started. Okay, so we're going to start, and there are 5 different types of chemical reactions we're going to talk about today. Now, again, this is just going to be the basics. There are some more types of chemical reactions we'll talk about at a later date, but for now, we're going to focus on the main 5. All right, so those main 5 are synthesis, decomposition, single replacement, double replacement, and combustion. Okay. So let's start with synthesis. All right, now for this, there is something I want to note. Some reactions are going to fit in perfectly into the categories here. Okay, so either synthesis or decomposition or whatever, right? Some of these reactions are going to fit, or actually most of these reactions are going to fit into a certain category and they are going to be that type. Some of them do not. All right, and we'll talk about how to kind of get through those that do not at a later time. All right, so let's focus on these. So I've got synthesis here. Now, synthesis are also called addition reactions. You can sometimes see them called combination and composition reactions. So just kind of keep a note of that. Typically, we refer to them as a synthesis reaction, but again, you could see one of the other types or one of the other names for this type of reaction. Now, for a synthesis reaction, what we're going to be doing is we're going to be taking 2 or more elements or compounds and combining them to form a single product. All right. So when we talk about synthesis, remember the word synthesis means to build or to create. And so what we're going to be doing is we're going to be taking these elements or compounds and we're putting them all together to make one single product. Okay. So that's kind of a big important identifier for a synthesis reaction is that single product. All right. So for synthesis reactions, there are some rules that you need to kind of keep in mind. And these rules are what are going to help you realize what to do for your products, like what product to create. All right. So let's go through these rules. I'll talk through them with you. And then we are going to actually work through these with you, or I'm going to work through these with you as well. So this first rule here says a group 1A or 2A element, which just means group 1 or 2 on the periodic table, may combine with a nonmetal to make a salt. All right, remember any ionic compound is classified as a salt, right? So we've got a metal and a nonmetal, we're combining them and we are making salt. Now, an example of this would be me taking a piece of lithium, okay, remember lithium's a metal, and we're going to drop it into a container with nitrogen gas. Okay, so we've got our metal, lithium, we've got our nonmetal, nitrogen gas, and what we're going to do is we're going to create salt. Now, what kind of salt? Well, it's going to be a salt between lithium and nitrogen, right? So how do we do that? So I've got lithium and nitrogen, so I'm going to produce lithium with a nitrogen bonded to it. Now, we do need to remember that if we've got charges, or anytime we're making an ionic compound, that we do need to cancel out those charges. Lithium's got a +1 charge, nitrogen's got a -3 charge. So I like to say swap, drop, reduce, where you swap their charges, you drop them low, and if the numbers are there to reduce, you reduce. So I get Li3N, all right? And then I would need to make sure that I go in and balance my reaction. So on the left side, I've got one lithium and 2 nitrogen. And on the right side of this formula or equation, I've got 3 lithium and 1 nitrogen. So I know that I'm going to have to balance this equation, right? Which for me is going to take a 2 right there and a 6 right here. Okay, so that would balance out my nitrogens, then that would balance out my lithiums as well. All right, so that is the first rule for a synthesis reaction. Okay, so let's take a look at rule 2. So in a synthesis reaction, if I've got 2 nonmetals, what they're going to do is they're going to combine to form a molecular compound. So here I've got carbon and oxygen. what's the most common molecular compound that is between carbon and oxygen? Well, it'd be carbon dioxide, right? So I have carbon and oxygen. CO2 would be my product. Now, looking at that, is that already balanced? Yes, it is. So I would know that that would be my formula. That would be the equation for this two nonmetals combining to form that molecular compound. Okay. All right. So moving on, next rule is two compounds combine to form a single product. Again, we know that synthesis reactions, we can have compounds instead of just elements, right? And so if we've got compounds, this is where things can this is where your rules are very important. So if I've got this, let's say I've got sulfur dioxide and it's passed over solid calcium oxide. Well, what I'm going to do is I'm going to make a product that combines those things. So remember, you always list your metal first. So I've got calcium there, and then I'm going to combine everything else, SO3. And so I would have calcium sulfite as my final product there. Okay. And again, it's very simple because essentially all you're doing is you're looking at, okay, this is a compound, this is a compound. All right. So what I'm going to need to do is just take all those things and kind of smush it all together. Okay. I've got calcium, Ca, and then I've got an S and 3 oxygens. Remember, S and 3 oxygens is sulfite. Sulfite has a -2 charge. Calcium has a +2 charge. They cancel out. We get CaSO3. Okay. So moving on, rule number 4. So rule number 4 says if I've got a metallic oxide, so metallic oxide would be me taking any metal and it's bonded to an oxygen. Okay, so any metal bonded to an oxygen, and I combine that with carbon dioxide, I will always produce a metallic carbonate. Okay, so a metallic oxide plus carbon dioxide will always produce a metallic carbonate. So what does that look like? So here I've got sodium oxide plus carbon dioxide. Again, I've got a metallic oxide, so sodium's my metal, oxide, plus carbon dioxide. That will always produce the metallic carbonate. So metallic, sodium, carbonate is CO3. We know that sodium has a +1 charge, carbonate has a -2 charge. Cancel those charges out, you get Na2CO3. Okay, so again, metallic oxide plus carbon dioxide will always produce that metallic carbonate. Okay, and again, if you look at them, essentially what you're doing is you are making both sides combine to form a single thing. So I had 2 sodium, I put 2 sodium over here. I had 1, 2, 3 oxygen, I put 3 oxygen over here. I had 1 carbon, I put 1 carbon over here. Okay, now that doesn't necessarily mean that that is always going to be how it is, but a lot of times that is what you will find actually is what your products will be. Okay, all right, so next, rule number 5. If I've got a metallic oxide, so again, any metal with oxygen, plus sulfur dioxide, okay, so SO2 instead of CO2, it is always going to yield a metallic sulfite. Okay, so here I've got strontium oxide plus sulfur dioxide. So I'm going to produce a metallic sulfite. So strontium, SO3 is sulfite. Strontium has a +2 charge. Sulfite has a -2 charge. So they're going to cancel out. So my formula here would be SRO plus SO2 produces SO3. Okay, so I have strontium oxide plus sulfur dioxide. That's going to yield metallic sulfite, strontium sulfite. Okay. Rule number 6. Rule number 6 says that if you've got a metallic oxide plus water, we're going to yield a metallic hydroxide. So metallic oxide plus water yields a metallic hydroxide. So here's my metallic oxide. Here's my water. Remember, water is essentially HOH. and it's going to yield a metallic hydroxide. So my metallic would be calcium. Hydroxide would be OH. I need to cancel out my charges. Calcium's got a +2. Hydroxide's got a -1. So to cancel that out, I have to put this in parentheses and put a 2 on the outside right there. Okay. So, moving on. Very last rule for synthesis. If I've got a non-metallic oxide plus water, it's always going to yield an acid. So a non-metallic oxide. So now we're looking on the right side of the periodic table to the right of those stair steps. And so, for example, carbon dioxide or sulfur dioxide or stuff like that, we're going to be, with water, we're going to produce that acid. Okay, so what do all acids start with? Well, hydrogen. Okay, and I've got CO2 and an oxygen there. So I'm going to produce CO3. Then I need to cancel out my charges. I've got hydrogen, which has a +1 charge. I've got carbonate here, which has a -2 charge. So it would be H2CO3. So that would be my acid. So I took carbon dioxide, that non-metallic oxide, plus water, and I produced carbonic acid. Okay, so that is synthesis. So again, synthesis, kind of the big defining characteristic of synthesis is we're going to be creating one product. Okay? All right, moving on, decomposition. We know that synthesis is to build up or to create. Decomposition is going to be the opposite, so to break down. So essentially with decomposition, we're going to be starting with one single reactant, and we're going to produce 2 or more products. So it's essentially the opposite of synthesis. Synthesis, you're taking 2 reactants and you're creating one product, versus decomposition, you're going to be taking 1 reactant and creating 2 products. Okay. So decomposition, again, it's a reaction where a compound breaks down into 2 or more elements or compounds. Typically, for this to occur, we're going to need some kind of energy applied. So that's going to be either heat or electrolysis, so shocking it with electricity, or a catalyst. What does a catalyst do? Remember, a catalyst is going to lower your activation energy, which means it takes less energy for that reaction to occur. Okay? So the nice thing about decomposition is it's essentially the opposite of synthesis. So if you can remember your rules for synthesis and then just flip them, then you've already got your rules for decomposition down. Okay? So let's go over some scenarios with decomposition. So I could take a compound and break it down into just 2 elements. So if I've got table salt, sodium chloride, and I send it through electrolysis. Sorry, struggling with my words there. So I send it through electrolysis. What's going to happen is that sodium and that chlorine are going to separate, and we're going to get a sodium and a chlorine atom. Now, when we do that, we do need to make sure we balance, and so that's what you see right here with our sodium chloride breaking apart into a sodium and a chlorine atom. Now remember, chlorine is a diatomic element, so we do need to remember to put that 2 as a subscript on chlorine when it's in the atom form. Okay? All right, moving on. So next, I have a compound could break down to produce an element and a compound. So that is a little bit different. So now we're actually taking one compound, but now instead of breaking it down into 2 compounds or 2 elements, we're actually breaking it down into a compound and an element. Now, an example of that would be hydrogen peroxide. Hydrogen peroxide will naturally decompose, but it will also decompose very quickly if we add a catalyst. And so what I'll do is I'll take that hydrogen peroxide, add a catalyst, and then I'm going to produce water and an oxygen. Okay, so in that case, we took a compound and we made a smaller compound with an element. Okay. All right. Very last scenario you could have, you could take a compound and break it apart into two smaller compounds. So in this case, we took magnesium carbonate and it broke down into magnesium oxide and carbon dioxide. Okay, again, took a compound, broke it down into two smaller compounds. So those are your scenarios. Now let's look at our rules. So if I've got a metallic carbonate, it's going to break down into a metallic oxide and carbon dioxide. Okay, that sounds very similar to a synthesis rule. So let's go back up to our synthesis rules. So I had a metallic carbonate, and it's breaking down into a metallic oxide and carbon dioxide. So in reverse, that would be taking a metallic oxide and carbon dioxide and creating a metallic carbonate, right? So rule number 4 is the same but opposite of that decomposition reaction. So that's something to keep in mind. Your synthesis and decomposition, they are essentially just opposites of one another. So if you can remember one, you should be able to know the other as well. Okay? Now, here we've got a metallic chlorate. Well, a metallic chlorate is going to break down. This is a different one from a synthesis rule. So a metallic chlorate is going to break down into a metallic chloride and oxygen. So metallic chlorate, an example would be sodium chlorate, so ClO3. It's going to break down into a metallic chloride, sodium chloride, and oxygen there. Okay, so looking at that, I have metallic chlorate. We've got a metallic chloride and oxygen. I would need to go in and balance, so I'd need a 2, and a 3 to get that balanced. Okay, next, metallic sulfites are going to break down into a metallic oxide and sulfur dioxide. Same kind of generalized idea as the synthesis, but opposite, right? So again, we took our, in synthesis, we took a metallic oxide and sulfur dioxide and created a metallic sulfite. But with decomposition, remember, it's the opposite. So we take the metallic sulfite and break it down to yield a metallic oxide and sulfur dioxide. So example, I like to use sodium just because it's easy to work with, but we'll use something else. So I have calcium sulfite, SO3. So that is going to break down to yield a metallic oxide, so CaO, and sulfur dioxide, SO2. Okay, I would make sure to balance. I've got 1 calcium, 3 oxygen, 1 sulfur. It's already balanced for me. Next, this one is again different from your synthesis. I've got hydrogen peroxide. Hydrogen peroxide will always break down into water and oxygen. So hydrogen peroxide is H2O2. It's going to decompose into water and oxygen gas. We would need to make sure to go in and balance, and that would be our balance. We have 4 hydrogen on the left, we have 4 hydrogen on the right, 4 oxygen on the left, and 2 plus 2 is 4 oxygen on the right. Okay, next, sulfurous acids decompose into water and sulfur dioxide. Now, if you look at that, we're taking a non-metal oxide and water, and remember in synthesis that made an acid, same thing here, but now we're doing it in the opposite direction because it's decomposition. So a sulfurous acid, so HSO3 is going to, H2SO3 is going to break down to form H2O and SO2. Okay, double check, make sure it's balanced. 2 hydrogen, 1 sulfur, 3 oxygen, 3 oxygen. Number 6, I've got carbonic acid. We're going to take that. It's going to decompose into water and carbon dioxide. Again, thinking about our rules, right? So I've got carbonic acid. H2CO3 is going to break down to produce H2O and CO2. It's already balanced for you. Last one we have here with our decomposition reactions is going to be hydrated salts. Now, hydrated salts are going to decompose into the salt and water. All right, well, what does it mean to be a hydrated salt? So let's say I've got something like copper sulfate. So CuSO4, and then it's got water attached to it. So it'll say 5H2O. Okay, now essentially what it's saying is I've got copper sulfate and there's 5 waters attached to that. And then when it decomposes, it's going to decompose into the salt, CuSO4, and 5 H2Os. Okay, so essentially all you're doing is you're separating out the water from there. Okay, all right, now here is what I will make a note of. While the new AP test, and we say new AP test because recently they changed it, the AP test does not expect you to remember a lot of rules, so have them all memorized as to what to predict in terms of products. The more you practice these rules, the more you know these rules, the more you learn these rules, the more comfortable you are going to be in the actual solving of the equations, solving of the problems, solving of, or just knowing what you're going to need to do with the information you're given. Okay, so I would highly suggest that y'all get these rules and at least have them kind of memorized because they are going to help you in terms of interpreting that content. Okay, all right. Moving on. So our next type of reaction is going to be double replacement. Now, double replacement is also called metathesis. So for double replacement, it's exactly what it sounds like. It's where we take 2 compounds and they're going to react to form 2 new compounds. How does that work? Well, essentially, you're going to take the compounds and you're going to flip their partners, is how I like to think about it. So all double reactions must have a driving force that removes a pair of ions from the solution. So it's going to have something acting on it to cause this to occur. Now, ions are going to keep their charges as the reactants and products. So I don't just take a sodium and it magically go from a +1 charge to a +2 charge. Okay, so they maintain the charge that they had originally. Okay, all right. So with double replacement, we've got a couple things that can happen. First off, we can have a formation of a precipitate. Now remember, a precipitate is that insoluble solid formed by reacting 2 aqueous solutions. So essentially what it is I take 2 things that dissolve in water, I mix them together, and I will create something that does not dissolve in water. So it becomes insoluble as a part of that reaction. Now, the 2 ion bonds together so strongly that the water actually cannot pull them apart. Because remember that how things dissolve in water is that the water molecules are actually going in, they're attaching to the positive and the negative sides, and they're pulling them apart. But when we form a precipitate, the bond is so strong between those atoms that the water is not strong enough to actually make them pull apart. Okay? So, how that happens. Example, solution of silver nitrate and lithium bromide. So I took silver nitrate, it dissolved in water. I took lithium bromide, it dissolved in water. When I did that, I swapped their partners, right? So silver was bonded with nitrate, and lithium was bonded with, I'll give you a different color. Lithium was bonded with bromine. Well, what happened? They swapped partners. So lithium swapped places with silver. And what we got is lithium is now bonded with nitrate, and silver is now bonded with bromide. Okay, so they swap partners, but as a result, we produced a precipitate, which is going to be, in this case, the silver bromide. And I know that because it says it's a solid. And it's a solid because it could not be dissolved by the water. Okay? All right, moving on. Next, we could have the formation of a gas. Now, gases may form directly in a double replacement reaction, but they could also result from the decomposition of a product such as carbonic acid or sulfurous acid. What does that mean? Well, what that means is that sometimes what you're going to have as a part of this double replacement reaction, you're going to produce something that would also decompose. And so here I've got carbonic acid. Carbonic acid we know decomposes into what? It's going to decompose into water and carbon dioxide. So that's what we should see if we've got that those special cases where we produce something that would decompose naturally. We would actually see that occurring as the products are being formed. Okay. So essentially what that comes down to, what that means for you is don't leave carbonic or sulfurous acid or ammonium hydroxide as a product in a double replacement reaction. You're going to need to remember to decompose them. Okay. So what do I mean by that? So I took excess hydrochloric acid and we put it into a solution of potassium sulfite. When we swap partners, so hydrogen is bonded with chlorine, potassium is bonded with sulfite. We come over here, they swap partners, so potassium is bonded. And normally you would say, okay, well, I'm going to produce H2SO3, right? No, you've got to remember that if I produce that H2SO3, if I produce that sulfurous acid, it's going to decompose further into water and sulfur dioxide. Okay, so these three compounds, we are going to need to remember that when they are produced as a part of a part of a double replacement reaction, they are going to decompose further. So anytime you produce carbonic acid or sulfurous acid or ammonium hydroxide, those three things are going to decompose further as a part of that double replacement reaction. Okay, so then let's look at this other reaction. So it says a solution of sodium hydroxide is added to ammonium chloride. When we do that, we're going to produce ammonium hydroxide, right? But we've got to remember that ammonium hydroxide is going to break down into ammonia and water. Okay, so that ammonium hydroxide breaks down into the ammonia and the water. Okay, so moving on. Next, I've got the formation of a molecular substance. Remember, molecular is going to be creating that covalent compound. Anytime we talk about molecular substances, we're going to be talking about covalent compounds. So here we've got lithium hydroxide and hydrobromic acid. So I took the LiOH, so Li and OH. Remember, you need to be looking for those polyatomic ions. And HBr, they swap partners. So lithium pairs up with bromine. Sorry, it should be red. So we've got our bromine, which was here. And my H2O, remember H2O could be rewritten as HOH. Okay, just as a kind of recognition of hydrogen and hydroxide. So I have my hydroxide from my LiOH, and I have my lithium from the LiOH, and they did end up swapping partners. Okay, all right, so that would be all of double replacement. So now let's take a look at single replacement. Okay, so if double replacement is taking two compounds and swapping them, right, swapping their partners and creating two new compounds, single replacement is going to be taking a compound and an element, and we're only going to have a single thing replacing. All right, so in single replacement reactions, one element is going to displace another element that is in a compound. So one element is oxidized, the other element is reduced. And we'll talk about oxidation and reduction a little bit later on in this unit. But in general, knowing that one element is going to be replacing another element is what you need to know for single replacement. Okay, so A plus BC is going to produce B plus AC. So essentially my A is coming in and kicking out that B, and then it's going to be bonding with the C, and B is going to be pushed out to the side on its own. Now for this, there are some activity series you need to keep in mind, okay? So active nonmetals replace non-active nonmetals. Active metals replace non-active metals. So when we're looking at this, we're going to be using our activity series. Now, on a periodic table, your activity series for your nonmetals is essentially just based off of where they are here. So as I'm moving down, my activity is going to be decreasing. So if I'm trying to see if bromine can replace fluorine, it cannot because it is lower on the activity series or lower on your periodic table. Okay, so you can do that with your non-metals. So here I took chlorine gas. It's bubbled into a solution with potassium iodide. So I'm taking my chlorine, which is a non-metal, and it's trying to replace my iodine, which is a non-metal. So the chlorine should not be trying to replace the potassium. Why? Because one is a metal, one is a non-metal. So my chlorine is trying to replace the iodine. So I need to look at my activity series. I have chlorine right here. I have iodine down here. Is chlorine higher on the activity series than iodine? Yes, it is. As a result, it can replace it. And so that's what we see happen. We've got our potassium bonding with our chlorine right here. And then the iodine is out by itself now. Remember, iodine is a diatomic, so you do need to remember to put that 2 on there. Okay? All right. Next, let's take that reaction and let's flop it. So instead, I've got iodine trying to replace chlorine in potassium chloride. Well, right here, I say it's no reaction. Why? Because again, I'm looking at my activity series. Is iodine high enough up on my activity series to replace chlorine? No, it is not. As a result, no reaction can occur. Okay? And then there would be our activity series. Now, if we're talking about metals, we do need to follow our activity series. You'll either be given a chart. You'll typically be given a chart similar to this right here to use on a test or quiz or something like that. So for my activity series, again, I'm trying to see if one is more active than the other, if a metal is more active than another metal. So here I've got magnesium. It's trying to replace iron. So I need to look at my activity series. I find magnesium. It's right here. I find iron. It is right here. So is magnesium higher on the activity series? Is it more active? Yes, it is. As a result, it can replace iron. So the iron gets kicked out by itself, and the magnesium is then bonded with my chlorine. Okay? Next, I took sodium and I added it to water. Well, what is sodium going to try to replace? Well, sodium is going to try to replace hydrogen. The thing to remember is that when we are looking at like that sodium replacing the hydrogen in water, this is something to take note of. Come on. This is something right here to take note of. So metals from lithium to sodium will replace hydrogen in water, whereas everything else between here and hydrogen, all of these will replace it in an acid. So these right here are going to be for hydrogen in an acid. These right here are hydrogen specifically in water. Okay? All right, so now let's take a look at this next one. So it says I'm taking copper and it's trying to replace hydrogen in water. And so we come down here and we find that copper is right here, which is actually below hydrogen. And so as a result, since it's got less activity, it's lower on the activity series, there will be no reaction. All right. So that is it for single replacement. Let's move on to our combustion reactions. All right, so the very last type of reaction is combustion. And remember, combustion is going to be taking a hydrocarbon, which is going to include carbon, hydrogen, and sometimes things like nitrogen or oxygen or phosphorus. And then it's going to react with oxygen, given some form of energy, typically fire, to cause a reaction to occur. Now, when that happens, we will always produce CO2 and H2O. So keep in mind that when we're talking about a hydrocarbon, a combustion reaction, you need oxygen, and then you will always produce CO2 and H2O. Now, for this, I do suggest when you are balancing your equations, balance the carbon first, then balance your hydrogen, and then balance your oxygen. So your oxygen should always be balanced last. Okay, every single time, if you've got anything else in there, oxygen should be balanced last. Okay, so here I've got ethane. Remember, ethane is C2H6, and then it's going to burn in air. So I have C2H6, and it is going to react with my oxygen in the presence of typically flame. And as a result, we will produce carbon dioxide and water. So the nice thing about combustion is your products will always be the same. They will always be carbon dioxide and water. Okay? All right. So that is it for combustion. So let's work just a few practice problems, and then I'm going to leave the rest of the practice for y'all to do. It'll be worked out on the key, so if you want to check your answers, you can check them. Okay? All right, so here we go. So it says sodium hydrogen carbonate and hydrochloric acid. They want us to write the balanced molecular equation for each. So I need to know what sodium hydrogen carbonate is. Well, sodium, and then I have HCO3. Now, hydrogen carbonate is also called bicarbonate, and it is going to have a charge of a -1. Sodium has a charge of a +1. So when we swap, drop, reduce, we're going to get NaHCO3. It's going to react with hydrochloric acid to produce. Okay, so let's take a look at this. So this is going to produce, so we swap partners. So sodium is going to pair up with chlorine. And then we would combine everything else. So H2CO3. But wait, H2CO3 is carbonic acid, right? So we've got to remember that it breaks down further. So this should be, instead of H2CO3, it should be H2O plus CO2. Okay, so then that would be my decomposition reaction. I would need to go back in and double check to make sure that I've got a balanced equation. So I have 1 sodium on the left, 1 sodium on the right, 2 hydrogen on the left, 2 hydrogen on the right, 1 carbon, 3 oxygen, 1 chlorine, 1 chlorine. So we would be a balanced equation, so we can go ahead and have that as our final equation. Okay? All right, so now let's take a look at this combustion reaction. So it says a combustion of ethanol, which is C2H5OH. They want the complete combustion of it. So I have C2H5OH, and its combustion, so plus O2, is going to produce always CO2 and H2O if it is complete combustion. So that's my formula, but now I need to balance everything. I've got 2 carbon on the left, 1 on the right, so I'm going to put a 2 in the front right here. I've got 6 hydrogen on the left, I've got 2 on the right, so I'm going to put a 3 right there. Now let's check our oxygens. 1 oxygen there plus 2 more is 3 on the left. And then I've got 4, 5, 6, 7 on the right. So I've got 3 on the left, 7 on the right. So what I'm going to end up doing is putting a 3 right there. That's going to give me 6 oxygen plus the 1 that's in ethanol. That would be my balanced equation. Okay? All right. So I'm going to stop there. I'm going to leave the rest of this for y'all to do. But hopefully y'all got it. If not, please reach out to myself or Mrs. Treese. And as always, hopefully y'all have a great rest of the day. All right. Bye, y'all.